These three quantities, because it is the cardinality of three different sets, should be somehow less than 16. You might think it is something strange algorithm, something weird, but you will see how beautiful the proof is. So you just so the algorithm is like you collect all of them, you make union of all of these Lij, but it is until J star. And then that's it. You get your clustering because you add it to your because your clustering is just the sum of these, and C is all of these sets. You put it inside this. So by after some time, you get all of the clusters. And so this is the picture. You have some. So this is the G plus bad. G plus bad. Remember, all vertices are inside this, except that we only accept the edges that are plus edges, E plus bad edges. So they have some connected components because we only allow positive bad edges. And then, for example, this is X, this is X prime, another one. And then going from SI, this is SI, going from SI to TI. For example, you go here, then you go here. After some time, you reach TI. So in the middle, because imagine that this is, you are measuring the length. This amount, until this. So the distance between SI and U, for example, your U could be here. So if distance between SI and U is J, then you have the layer so this is a layer. This is another layer because the distance is something else. This is another layer, something else, until we reach that final terminal, which is TI. So I want to say that for every I from 1 to k, it is enough to prove that distance between SI and TI is greater than root of n minus 1. The proof is very simple because we assume SI and TI are in the same connected components, X disconnected components. And so we write DUV. Remember that these are, each of them is less than 1 root of n. So this is greater than d of SI and TI because it's the shortest path. We just use the triangular inequality. And then by definition, you know that this is greater than 1 minus 1 over n. Because SI and TI are such that they are greater than, because SI and TI is inside E minus bad. And in that place, you have such a distance. So here you simplify this. You add this. You just add this. So you sum this, and then you get, because most of them are 0, so we only we filter, and what remains is just excluding e plus 0. And what it means? It means that 1 over root of n plus 1 over root of n. How many vertices are there? There are n, at most n vertices. So this is n times 1 over root of n. And this is 1 square root of n. So the distance between them, distance between Si and Ti, is at least square root of n minus 1. So we have proved the lemma 1. And then you will see how to use, if you read that paper, you will see how to use this important thing, lemma 1, to prove that the algorithm can be a good rounding for root n approximation. And that's it. Have a great weekend.